We're super happy to have Oliver Schlotterer, and he will tell us about integration on higher genus Riemann surfaces and string amplitude.
Okay. Thanks a lot for the kind introduction. So in this talk, I want to present the math problem of performing integrals on higher genus Riemann surfaces. And I want to argue that this math problem is in a fruitful symbiosis with string scattering amplitudes. So this is material drawn from joint papers with mathematicians, Benjamin Enriquez and Federico Zerbini, and with physicists, Eric Doker and Martin Hilling. But apart from thanking my collaborators, I would like to send most of my thanks to those people who made it possible that we are meeting here this week. So as the last speaker of the conference, it's my particular honor to send a big, big thank you to all the organizers. Please join me for the applause. And we should particularly thank Magdalena, who dedicated the largest chunk of energy and time to all of this. Good that you're close enough for a high five. Fantastic job, Magdalena. And there are many other dear colleagues who are not working full-time as scientists, who are absolutely essential for the success of this event here. So also big thanks to Jimmy, Olga, Anastasios, Elvira, Hans, and possibly people that I forgot. Okay, I understand that this is the last talk between the end of the conference and you. So let me try my very best to be gentle. I think I should dedicate at least half of the talk to motivation and context. So once more, we want to integrate on higher genus Riemann surfaces, and I owe you some explanation why. And then in the more technical part of the talk, I will introduce the specific protagonists who do integrations for you, namely polylogarithm functions on these Riemann surfaces. And I will try to make some connections with string scattering amplitudes. So the motivation for this talk, for me personally, it begins in the high school days. When we learned about calculus, our math teacher told us that doing integrals is much harder than to do differentials. And as a teenager, I found this pretty frustrating. Well, I still find it frustrating nowadays. So the goal of the talk is to mitigate this a little bit. So here's an example for this kind of inequality. Take a rational function, r of x. Taking its derivative will surely be rational, no doubt. But if you take an integral of a rational function, even in an innocent example like 1 over x, then all of a sudden you're out of the realm of rational functions and you get some more funky things like a log. But adjoining the log alone is not enough to complete the rational functions under doing integrals, because if you integrate the log further, maybe with more rational stuff, then you get yet another new function known as Li2. So clearly this is a never-ending story. If you want to complete the rational functions to close under integration, then you need more and more special functions that generalize the log in Li2. And even though that function space is infinite in size, there are still good organizing principles to work with it quite efficiently. So the completion for the rational functions are known as multiple polylogarithms, and they are here defined recursively. Start with the trivial polylog, where you have an empty set left of the semicolon. This is 1. And whenever you want to add variables that are tracked on the left of the semicolon, you do an integral, essentially against a simple pole or a d log. And here the integrand is a shorter MPL. So this is really a recursion in the number of entries here. And clearly, some of the functions you know and love are part of this family. To introduce a little bit of jargon, I will repeatedly speak of integration kernels for various geometries, including higher genus Riemann surfaces. And whenever I say kernel, I mean these things whose iterated integrals you take. Okay, the geometry for the content of the previous slide is the Riemann sphere. Because what we did is we take rational functions that naturally live on the Riemann sphere and we completed them to be closed under integration. And I should add, these polylogs are the smallest function space to do you the favor of closing. I mean, we want to work with a function space that is controllable. We don't have any kernels with a double pole, triple pole, quadruple pole, simply because we don't need them. You can use IBP, integration by parts, and make sure that at the end of the day, you get away with rational functions and these polylogs, which are iterated integrals over simple poles, as opposed to higher order ones. And they close not only under integration in Z, which is somewhat obvious from the definition, but they even close if you integrate in these P variables here. This is a little bit harder to see, and in one way or another, you need partial fraction to make that happen. If time allows, I tell you about higher genus version of this partial fraction relation. Yes, please. Oh, sure, there can be divergences for all kinds of choices. And don't worry, there is a well-understood regularization prescription. Whenever some of these integrals diverge at the endpoints, there are ways to nevertheless work with them and have algebraic properties like shuffle relations go through, also in the divergent cases, which can be regularized like such. Okay, so these polylogs are the way to deal with integrals on the Riemann sphere. But what if you plan to integrate on a more complicated geometry? So let's make sure that complication grows in a bounded way. After the sphere, as string theorists, we want to next look at the torus and see what happens if we attempt to do integrals there. So here on the torus, the name of the game is to integrate rational functions in two variables, x and y, subject to this polynomial equations here. That's the hyperelliptic representation of the torus. And one way of proceeding is to change your alphabet of integration kernels. No longer the dx over x minus p only, but also you need square roots. I mean, all these y's downstairs, they are, if you solve this equation, a square root of a degree 3 polynomial. So taking iterated integrals of those kernels here gives rise to the space of so-called elliptic multiple polylogarithms, again designed in a way that they close under integration. And there are many, many ways of spanning elliptic polylogs, and here's just a small sample of possible references where you can read more about them, written jointly by mathematicians and physicists. Okay, after the torus comes, at least to my taste, the higher genus Riemann surface. So this will be the main objective of this talk, to give you means of doing iterated integrals on a higher genus Riemann surface. Let's take the genus to be arbitrary H. And perhaps it was a little bit misleading to point out hyperelliptic representations, because such a polynomial equation only covers a subset of the moduli space of higher genus Riemann surfaces. But the results you're going to see, the results won't involve these polynomial equations and will be valid throughout moduli space. Also the non-hyperelliptic surfaces that arise starting from genus 3. But a big word of modesty, this talk is not attempting to deal with higher dimensional varieties. I mean, by sticking to Riemann surfaces, we only deal with geometries whose complex dimension is 1. But ideally, we would like to deal with integrals also on higher dimensional varieties, such as K3, Calabi-Yau, and more, and that is left to the future. So the exercise of getting integrals under control on Riemann surfaces is, if you wish, a temporary step in the bigger research agenda of doing integrals on arbitrary geometries. Good, this was the computational prelude. It's time that we talk about physics. So the overall slogan is that scattering amplitudes are a context where your integration skills are converted into physics insights. One example being the Feynman integrals that are ubiquitous in quantum field theory scattering amplitudes and also in those of perturbative gravity. And here are a couple of scenarios where it's important to be able to integrate on non-standard geometries. For instance, for certain standard model interactions, such as TT bar production or Müller scattering of electrons, you should be able to deal with Riemann surfaces of genus 2 and higher. So there are specific two-loop processes experimentally relevant, where the answer is, in one way or another, a genus 2 polylogarithm function. And as a motivation for the higher dimensional geometries, sadly not covered in this talk, I was surprised that the amplitudes community produces publications in Nature. So this was about gravitational precision computations. I think the 5th post-Minkowskian order for certain non-conservative black hole observables. And there you find Calabi-Yau geometries in the multi-loop Feynman integrals. Now, apart from QFT, there is another physical theory we like very much, where integration on higher genus Riemann surfaces matter, and I will zoom more onto that. But I also speculate for myself that being able to integrate on Riemann surfaces, it should be pretty universally applicable. So maybe sooner or later we hear from other fields outside high energy physics where people might be happy using such polylogarithm functions. Okay, so some string theory motivation for this talk. String amplitudes in the perturbative sense are naturally arranged in terms of Riemann surfaces with marked points for the external states. You're supposed to integrate over the full moduli space of these punctured surfaces. So for each external state, there's a marked point to be integrated over. And there are many reasons to know about polylogarithms if you want to get information out of these moduli space integrals. So for instance, if we go for tree level, the sphere with marked points on it, then these integrals can be evaluated order by order in alpha prime in terms of so-called multiple zeta values. These are polylogs at special points, z equal 1 if you wish. And even if the answer is just numbers, namely multi-zetas, it's really valuable to know that intermediate steps, when you integrate one puncture after the other, you have some polylogarithms in the intermediate steps. So this information, for instance, reveals that closed strings are single-valued open strings. This is a certain number theoretic rule, how the multi-zetas in an open string calculation is projected to those multi-zetas that survive in the closed string result. And this is a well-established story in flat space-time, but recently these ideas evolving around single-valued multi-zetas have propagated to ADS. Really impressive literature over the last years, many authors. And it's great that we saw a poster from Aurélie about that. And here I'm highlighting two recent papers on that subject of string tree-level amplitudes in ADS, where tremendous progress was made. Yeah, also the author here, Konstantin Baune, is in the audience. Okay, so this is a tree-level incarnation, how polylogs help you alpha prime expand string amplitudes. And similar statements go through for genus 1. So for instance, if you want to know the effective actions and loop-level contributions to them, perhaps as a practitioner of S-duality, then it's really good to have elliptic polylogarithms in your toolbox. And yeah, techniques derived from elliptic polylogs were essential to harness the so-called modular graph forms that are, if you wish, the key steps towards getting r to the 4 and d to the n r to the 4th interaction out of that diagram. Yeah, there was also a poster by Johan Sohnle on this circle of ideas. Good. As I just said, polylogs are useful to integrate over the marked points, but slightly paradoxically, polylogs are even good to learn about the integrand, even if you haven't started to integrate yet. I mean, these innocent-looking diagrams, they represent conformal field theory correlators of all the vertex operators, which insert the physical states on these world sheets. And for superstrings, the correlation functions starting from genus 2 become fiendishly hard, at least if you want to have them in a form that is amenable to low energy expansion. And I believe that the integration kernels that you will see today will be essential to run bootstrap programs to determine the correlation functions for multi-particle cases and multi-loop amplitudes from some general properties and consistency checks. So in that sense, the techniques evolving around polylogs are useful for both the integrand and the integrals within string scattering amplitudes. Yeah, and as you can see from these two examples at bullet points, there is in general a really good symbiosis between concrete questions arising in string amplitudology and some mathematical developments somewhere in between number theory and algebraic geometry. This brings me to the end of the more motivational part with a general context. And now I will proceed to a slightly more concrete discussion of higher genus polylogs. It's a good time to ask a question if you have something urgent on your lips. Okay, then let's go into the hands-on part. Notation for Riemann surfaces of genus H is this sigma. Here's a cartoon in the genus 2 case. And the one-form cohomology will always have a couple of abelian differentials. These are holomorphic one-forms. It's a total of H of them if you are a genus H. You can pick some normalization conventions using the A-cycle periods, but then you can't control the B-cycle periods. So it's these capital omegas, the period matrix entries, which represent the complex structure moduli of the surface. And in the context of integration kernels, these abelian differentials, they are a must. They will be among our integration kernels. But as you can expect from genus 0, for the first polylogs you saw, they came from integrating simple poles. We also want to do that at higher genus, so there must be some singular kernel besides the abelian ones, which are holomorphic. But the omegas and simple poles themselves are not enough. I will argue that you will need many more kernels to really ensure that the polylog function space closes under integration, which was the initial selling point, what these function spaces should do for us. And whatever comes beyond, the packaging device for the rest of the talk is a flat connection. Let's package the integration kernels here and those and whatever else it takes into a big connection J, valued in some Lie algebra, and as a starting point to construct good spaces of iterated integrals, we should make sure that this connection obeys the Maurer-Cartan equation. So here, flatness condition. Okay, so handing you a flat connection is more or less as good as telling you how the polylogs are constructed. Now, what kind of properties would we want to see from our integration kernels and their flat connection? Well, a natural wish list after having seen the genus 0 case is meromorphicity would be great, single valuedness would be great. I mean, dx over x minus p is single valued, and at most simple poles would be great. But these properties don't go well together starting from genus 1. For instance, you probably know that story about the Weierstrass P function. It has a double pole, it's elliptic, but it doesn't have an elliptic friend with just a simple pole. So that's the counterexample already at genus 1, that you can't have these three pleasant properties at the same time. And I'm personally, well, emotionally quite attached to the third property. I will only present connections that obey the simple pole criterion. And then there are two options. Whom do I sacrifice? I will give you a non-meromorphic connection, which has single-valued kernels. And independent on that, I will give you a meromorphic connection where we sacrifice the single-valuedness with respect to the homology cycles of the surface. And either way is fine. In the end, you span the same function space of polylogs, no matter if you follow the single-valued route or the meromorphic one. Okay, so these were the generalities, and I will now go for the single-valued connection. Just with simple poles, but no meromorphicity, unfortunately. And the central Lego brick to derive the entire flat connection is the two-point function of the free boson on the genus G surface. So all of you who have experience with worldsheet calculations will recognize the logarithm here. On the sphere, the two-point function of the free boson is just the log and nothing else. But once you are on a torus or a higher genus surface, you need to add something to make that single-valued. Single-valued under moving the points around the homology A and B cycles. I don't think I want to show you the explicit construction here, how to do this plus single-valued completion, but it's a pretty well understood process involving theta functions, prime forms, and more. And in fact, we can completely bypass the details of the single-valued completion. You can characterize this Green's function by three properties. Namely, being symmetric in the 2 points, having a nice Laplace equation that reflects the log behavior, and integrating to 0 against a specific volume form kappa. By the way, I will use Einstein summation conventions here and there, and whenever you see upper indices, I'm cheating in some inverse of the imaginary part of the period matrix, just as a small confession about the notation and use. Okay, so summary of that slide, there exists a well-understood Green's function on 2 copies of the surface, and that one I will now use to construct a flat connection for higher genus polylogs. I promised simple poles, and an easy way of getting simple poles is to differentiate the log. So here the Green's function representing the single-valued flavor of the log. So this is probably the term you expected, but you need a few more kernels to make sure that the polylogs close under integration. So this is not yet visible from the material here. Just trust me that you need an entire matrix worth of integration kernels that accompany this simple pole here. So it's a matrix with indices I and j, both of which run from 1, 2, ... all the way to the genus of the surface. So for those who work a lot on the torus, then you won't recognize the first term, because this term trivializes on the torus, because as a 2 tensor, this is traceless. Okay, so we start with a matrix worth of integration kernels that contain the simple poles. And now on top of that, for closure under integration, we need even more integration kernels. And everything higher, we generate recursively by doing convolutions. Has a similar flavor as the iterated integrals we will eventually do, but notice that here is a surface integral over the Riemann surface. So these f's are 1,0 forms in the integration variable z. So we need to get a 0,1 form here to make this a volume form, to make this something that we can meaningfully integrate over the surface. And as you know from convolutions, they tend to make things less singular. So while the 2 index f has a simple pole, all the f's with more than 2 indices are completely regular throughout the surface or throughout the 2 copies of the surface where the points x and y can live. So Fij is the only case with singularities. And yeah, as I promised, they're not going to be meromorphic. So here is a kind of recursion under doing anti-holomorphic derivatives in the point x. Good. Let's now assemble the connection. The previous slide provided for you an infinite tower of tensors denoted by f with more and more indices I upstairs, all of which run from 1 to 2 ... to the genus H of the surface. And we are now decorating them with certain non-commuting bookkeeping variables. There is an A variable, and there are B variables, both here and there, entering through adjoint actions. So everything in red here, these are non-commuting variables. In mathematical terms, they are generators of a free Lie algebra. So you just need to know all the words in A's and B's are independent. No relations whatsoever. So good news, you can then, by taking coefficients of these words, extract all the tensor components that you may want to look at. Okay, so I confess that the Fs are not meromorphic, but this is a feature rather than a bug. By this property of the F tensors, one can show that the connection here is flat, that it satisfies the Maurer-Cartan equation. This in turn means that you can put it into path-ordered exponential. You look at the solution to the differential equation, d of that is the flat connection times the same pxp. So this is defined as a series of iterated integrals. Here we integrate the connection once. Here is a double integral, and I leave it to your imagination how it goes on. So this is completely explicit since you know what the connection is. And since the connection expands in A and B letters, the entire pxp can be expanded in the alphabets of A's and B's. So now we define higher genus polylogs gamma as the coefficients of that pxp when you extract a particular word in the A's and B's. So here's an example along with a two-letter word, and typically you mix integrals with different numbers of iterations, coming from the fact that flatness arises from both the dj and the j wedge j term. So connoisseurs of the Brown-Levin elliptic polylogs from genus 1 will recognize this object here. Okay, concerning the modular properties. Well, the moduli space integrand for higher genus string amplitudes enjoys an invariance under the modular group SP2H, Z. So here, this amounts to changing the basis of homology cycles such that the intersection pairing is preserved. Under these modular transformations, the Green's function is invariant. Remember, the Green's function was the central Lego brick to construct everything else by derivative and convolution. And correspondingly, the Fs are modular tensors in the sense that if we do an SP2HZ transformation with this block form, then all the indices get matrix multiplied with these automorphy factors C omega plus D. So at genus 1, these are the famous C tau plus D factors. And there's also an inverse for the lower index. So the integration kernels have excellent modular properties, and the entire flat connection is modular invariant if you prescribe A and B to transform. So the good news is that not only the Fs, but even the polylogs generated from the Fs are modular tensors. So you can really control how they behave under modular transformations. Now I'm wondering, Pavel, what's the timing? Okay, good. Then I should be quick in presenting you the alternative. So if you are a more meromorphic person and don't insist on using single-valued kernels, here is an alternative to span the same space of polylogs. And that alternative was already in the math literature from 14 years ago by our collaborator Benjamin Enriquez. He showed the existence of a flat connection with pleasant properties. He indirectly defined functions g, which have the same enumeration like the Fs, but which are meromorphic and have good monodromies in the sense that moving a point around the A cycle is trivial, and moving a point around the B cycle is somewhat covariant in the sense that the right-hand side, all the B monodromies, are expressible in terms of the same family of kernels G. Okay, this math paper is really seminal, but sadly it didn't give us an explicit construction. So clearly the physicists were pretty hungry in getting something hands-on, an explicit version of these Gs. And the first group to succeed is the Zurich group, represented by Konstantin in the audience. So they constructed the G kernels using Poincaré series, for hyperelliptic locus on the moduli space. Then a second construction of these Gs takes a detour through the Fs. So I told you about this flat connection to generate the polylogs. And if you do a gauge transformation of that, you eventually get to the generating function of the Enriquez kernels, the meromorphic ones. So the details are a bit nifty, that you need to do a Lie algebra automorphism along the way, but it can still be worked out order by order without any obstructions. So this is second explicit construction. And for timing reasons, I won't show you the details of a third explicit construction, but let me just say that the G-kernels, the meromorphic ones, can be obtained from the prime form and certain acycle convolutions thereof. Okay, so there are these meromorphic friends G that have similar properties to the F tensors from before, and which we can use to construct higher genus polylogs. And we don't have to worry about homotopy invariance. We don't need to extract words in A's and B's of a bigger object. We can just do iterated integrals of the G kernels as they are. So there's a bit of multi-index notation that you need to make this pretty. But yeah, so let's say these are the meromorphic formulations of the higher genus polylogs. And as I said, equivalent to the construction from the F tensors that you saw before. Good. This is a strings conference. So let me again connect with the concrete tasks in string amplitudes. As I emphasized before, this Green's function here, which was at the beginning of constructing the F tensors, this is a two-point function in the conformal field theory of the free boson. It, for instance, enters the ubiquitous Kober-Nielsen factor, which you will always meet in genus G endpoint amplitudes. No matter how complicated the supersymmetry details of RNS or pure spinors are, you will always have this Kober-Nielsen factor. So this Green's function is all over the place. Now, if you do superstrings, say in the RNS formulation, there's also a worldsheet fermion that you have to wrestle with. So what kind of gadgets do you get from the correlators of the fermion? And this is a natural arena to get either the F tensors, built from surface integrals of the Green's function, or from the Enriquez kernels, obtained from A convolutions of the prime form. You have the choice whether you prefer using the F's or the G's. Both of them are natural languages to take care of these fermionic correlators, namely to capture all the dependence on the marked points here. So for that reason, since the F tensors and G kernels appear naturally from fermion correlators, for that reason, we expect that everything else in the integrand for string amplitudes is expressible in that language. And there are also some selection principles up to how many indices you need to go once you fix the genus, once you fix the multiplicity. Okay, I think in practice, I should be careful about things that go beyond genus 3. I mean, I don't want to question the non-splitness result of Donagi-Witten, but the concrete construction sites that we have on our bucket list for the next 2 or 5 years is to try our luck at genus 2 and 3 at the endpoint level, how we can do bootstrap programs based on these F and G kernels. But yeah, originally, these kernels F and G are designed to do integrals for us. So clearly, they will be pretty useful to do the integrals over the marked points here in an alpha prime expansion. Sorry, I forgot to put an alpha prime into the exponent. Each order in alpha prime will have an extra function of a factor of Green's function that you should be integrating. But so far, this setting of polylogs is not yet there to integrate over the complex structure moduli. So fortunately, we saw in the talk of Lorenz Eberhard that there are really, really beautiful methods under development to deal with integrals over tau. So I believe this program of the authors here, it is perfectly suited to be generalized to higher genus, and that's something really important. Good. Then in the leftover time, I will talk a little bit about the closure under integration. So this was the selling point I made at the beginning. Why polylogs? Their raison d'etre is that they should give us a function space that closes under integration over points. And I want to at least indicate why these F and G kernels do the job. So here's again the recursive definition of higher genus polylogs in the meromorphic formulation. And it's pretty obvious that they close under integration over Z if you only look at products of such a gamma twiddle and a G. So a lot of primitives in Z come for free by definition. But let's now look at the less obvious parts. Maybe you want to take a product of gamma twiddle with such a kernel, which is a one form in P, and then ask for integration over P rather than Z. So these delicate cases, when you don't do the obvious integrals, they require some functional identities of these kernels. So here's one example. What if you integrate a gamma twiddle not only over a abelian differential, but also over a meromorphic kernel that depends on Z? This doesn't fit to our definition yet, but it starts fitting the definition once you use this interchange lemma here. So the left-hand side is nasty because Z appears in two factors. But the right-hand side is much more friendly for integration over Z because only one of the factors depends on Z. And you can use the definition of gamma twiddle. So this was just a warm-up example how kernel identities are essential to implement the closure of the polylogs under integration and really to derive practical algorithms. So here's another example of such a functional identity, and they are more complicated identities which also have free indices I and K here and involving 3 points. So this is what I advertised at the beginning as a higher genus incarnation of partial fraction. So at genus 1, they are literally the Fay trisecond identity, and in view of the parallel with the genus 1 case, the identities like here are sometimes referred to as Fay identities. And in fact, it doesn't matter whether you work with the single-valued F kernels or the meromorphic G kernels. These functional identities on the slide are all identical. So as you just saw, I renamed G into F, and all the identities are still true. Hence, the integration algorithms I advertised will take an almost identical form, no matter whether you use the G's or the F kernels. And here is the showing off slide, just to convince you that this can be done for an arbitrary number of indices. Maybe you need combinatorial tools like a shuffle product, but this can also be done, this can all be done nicely and recursively. And yeah, the proof for this equivalence FG was also done by the Zurich group. So please don't let Konstantin escape. Chat with him after this talk. Good, so these are the mechanisms that make sure that the polylog spaces close under integration as promised. Good, time to wrap up. I gave you 2 constructions of polylogarithms on higher genus Riemann surfaces. You can choose between single-valuedness or meromorphicity, or you work with integration kernels that have higher poles. I haven't been brave enough so far. And the connection to string theory comes about from the Arakelov-Green's function, namely the 2-point function of the free boson, which is all over the place in scattering amplitudes of arbitrary perturbative string theories. So we constructed these F tensors, which were the integration kernels. They arise really natural in the worldsheet CFT. In particular, the worldsheet fermions of the RNS superstring, their correlators are particularly natural to be expressed in terms of the F tensors that don't simplify to Arakelov-Green's functions themselves. And for alpha prime expansions, yeah, we are in a good position now. We can, in many cases, use the definition of polylogs or use integration algorithms based on Fay identities. And for closed string alpha prime expansions, we will also need to look at single-valued versions of these higher genus polylogarithms. Yeah, so there's a lot to do. I hope I gave you a glimpse of what has been done and what will keep us up at night for the next years. Thanks a lot.
Thank you so much for this beautiful talk. And we have time for questions.
Yes, thank you for the talk. And so h equals 0 case, the simplest the example beyond the rational case is the log dx over x, and h equals 1, you put the square root of a cubic polynomial, and just the simplest example h equals 2, what you put there, without the listen so many indices, just one example.
Okay, yeah. So disclaimer number 1, all the formulas in the second part don't apply to h equals 0. Don't try to recover the sphere case from them. Then if you specialize this formula to h equal 1, then clearly you won't get these kernels in an obvious way. It's pretty non-trivial to work out the dictionary between these kernels from here and the kernels from there. And I think the key paper which made that possible is that one, Brödel, Dua, Dulat, Tancredi. They established dictionaries between different integration kernels for elliptic MPLs. And frankly, the higher genus version of the dictionary is an open problem. So I think that's a pretty pressing one, really interesting one. I wish I had a solution for that.
Thank you for the nice talk. I have a sweet feeling that I understood more than usual in this subject.
Pleasure to hear.
I wanted to ask you, once one sees the Lux connection which you wrote, I mean, Cartan-Moore or Lux, one wants to quantize it. Do you know, like we do, for example, in finite gap method, yes, this Lux connection is a starting point for quantization, so from classical curve to quantum spectral curve, etc. Could you imagine something like that here and some quantization of these polylogs, etc., or it's too exotic?
Oh, yeah, I heard people discuss that, yeah. I'm lacking the expertise to give you a qualified answer on the spot, but I think it could be an interesting research problem to try getting towards a higher genus Calogero-Moser system based on some of the ingredients here. But I wouldn't know how to do that.
Thank you.
Are there a simplification for hyperelliptic curves compared to generic?
I fully agree, yeah. So that's a particular motivation to tackle the attempt to set up the dictionary in the near future. At genus 2, for instance, the natural integration kernels will also have a x squared dx over y, x cubed dx over y. I think a first step is to translate all of these into the Enriquez kernels in F tensors and to see what the simplifications are. I don't have much intuition about that. Or maybe Konstantin, can you comment?
So we also looked at periods over these polylogarithms, so a-cycle integrals. And there we see that there are certain identities which only appear for hyperelliptic curves. So there seems to be some special cases when you have an hyperelliptic curve instead of something which is not hyperelliptic. So I guess the hyperelliptic involution might play a role in simplifying things.
Thanks.